So we were, to recap on what we have done the DES and its analysis with respect to its structure and the necessary ways in which the keys are generated, the expansion box, the S box, how they are worked with, how individual rounds are working in terms of the Fiestal cipher. So those things we have discussed. And based on that, in last day's class, we had explained to certain numericals that how or what are the type of numericals you are going to expect in your questions, in your exams and all. And in all that, we have observed that the findings are it should be repeated in every round, irrespective of which round we are giving the questions. But there are certain properties which you need to keep in mind, especially the portion of parity bit. If you remember, we had done something of this nature. This kind of a question we have done, in which how the 64 bit is converted to 56 bit, how the 56 bit is converted to 48 bits. So suppose you are given a 56 bit, you should know the process of converting that to 48 bits using the table and the information provided, right? So based on that, as I said again, please go through these examples and the detailed solution which I provided, which is absolutely same as that of what we have done over here. This is taking a different example and the same procedures will follow. So please do that. So today we are going to start with the last segment of DES and we'll start with the AES as well. Because AES, as I already had informed you, that this is AES is the better version that is being used from 2001 onward. So there must be some reason for why it is being used. And the reasons behind that is the DES analysis, in which we are going to focus on the different weaknesses or the drawbacks, if you say, of DES. And in that, the first thing that comes in mind, the two things that we need to take into account. First of all, see, the point is, we already had, I think I have already touched upon that point in the very first day when we started off with DES, that one of the primary problems with DES is that it is of 56-bit length. The key size is of 56-bit length, and that is one of the issue, because at the point when DES was conceived, the idea, at that time the parallel processing and all those stuffs were not there. Hence, it was thought of that 56-bit it will be very difficult to crack and all those things. But now, naturally, with the advent of more and advanced technology, it is very easy to crack, and that's why the 56-bit is not adequate. Although there are two other versions of DES which is available. One is called double DES. There is something called as triple DES also, in which we are going to use multiple keys, K1, K2, like 56-bit for K1 and 56-bit for K2. So like that, it is also is there. Like two DES ciphers, suppose 16 round will be appended together. So there are processes like that. But given the fact that we have AES right now, it's immaterial to discuss all those processes as such. Okay, so that's why we are not going to discuss on double DES or the triple DES for that matter, as it's not there in our syllabus also, to be honest. But those are the things you can look into later as well, which involves a little bit of redundancy or a bit more security, I would say, compared to the conventional DES. But as we are now rightly pointing out, one of the important factors are the two important properties of DES that we are going to check. The first is called as the avalanche effect, and the other one is called as completeness. Now, in case of avalanche effect, what happens is that for DES, the avalanche effect of the property is rightly justified, because it means, what does avalanche effect mean? Is that it means small change in the plain text would result into a significant change in the ciphertext. We'll take an example in next slide to understand this. But for the timing, it is just the definition of an avalanche effect. That if you have small changes, suppose 1 bit change in the plain text, it should have a significant change in the outcome. And in DES, we can prove it. In fact, if we take an example and we can do it for 16 round, that actually happens. Alright. So to understand that, let me go back to avalanche first and then I'll come back to completeness for that matter. So let's take this as an example. This is the example of avalanche effect I'm talking about. Why for DES it is much better. You can see over here what happened is that we have a plain text which is having all zeros, and the second one which is here, all zeros which is here, and there is another plain text which has only 1 bit change. Rest of the things are same. Except that the 1 bit has changed. Only 1 bit. Okay. Now, in both the cases, what is happening? We are using the same key. Over here, you can see the same key has been used in both the cases. And if we go on doing it for both the plain text for 16 round of calculation, we can find out, you can see over here that for the round 1, there is in the bit difference is 1. But when we go to 16th round, it will be around 29 bits will be different. So for a 1 bit change in the plain text, there is a 29 bit change in the final ciphertext. Because remember, the in-between changes is our concern. We are mostly bothered with first and the 16th. Okay, so that's basically what the idea behind E is. So with respect to avalanche effect, we are observing that for only 1 bit change, there is around 29 bit that is getting changed, which is around 45% of the change that is happening, which is significantly high. That is why we can say that for DES, the avalanche effect is pretty good. Like there is a significant change that happens for the ciphertext, given that we have changed only a very small change on the plain text. Got it? So that's the example and the explanation to it. The other one is the completeness that I'm talking about. And this in fact means that each bit of the ciphertext needs to be dependent on many bits of plain text. Alright, so this is another property which can be explored, that what is the analysis, and in that also it fails a little bit in case of DES, that how many bits of ciphertext, like you can see the point that is highlighted, each bit of the ciphertext needs to depend on many bits of the plain text. So that is one of the properties that is usually considered for the DES. But the major problem that comes in is given in this particular slide. Alright. Now, if you remember, in case of DES, one of the factors or the pivotal attribute, I would say, is called the S box and the P box. Every now and then, this S box and P box will be coming in, and they are the primary contributor to the randomness to the data. Right? So that's what we have done. So if you observe that in case of S boxes, the design provides the confusion and diffusion of bits from each round, whereas the P box creates the diffusion of bits. Now, even a number of rounds, DES uses 16 rounds of Fiestal cipher, but even in doing that, there are certain attributes of the weakness in S box, weakness in P box, and weakness in the key. The third point is actually one of the biggest drawback of it. It comes back again down to the same line, that 56-bit key is not sufficient. So these are the primary problems which we are going to address for the time being: weakness in S box and weakness in P box. So to understand that, we will see the weakness in key later separately. So weakness in S box is given over here. As you can observe, the S box 4, the fourth S box. Remember, I told you that there are 8 S boxes which are present in DES, and each of the 8 boxes will have a certain table associated with it. And when you are looking at closely to S box 4, this is the table given for S box 4, if you can observe. And very interestingly, if you observe that as per the design rule, the last 3 bit, 7, 2 and 14, is almost repeated over here as well. Alright, so in case of S box 4, the last 3 bits can be derived in the same way as the first bit. So it is somehow confusing in that way, that how this can be made to work in a DES, but this was later found out. When it was analyzed, it was found out that the table has some fault. Another fault it was addressed, that 2 specifically chosen input, like it is a possibility that you are giving 2 inputs. Remember, we had in S box, we were giving 6 bit at a time. So given that 6 bit, you are having a scenario, you might have a scenario that you are giving 2 chosen input and you are getting the same output. Although different inputs you are giving, but you are getting the same output out of the tables which you are going to use for the S box. Not only S box 4, but the other rest 7 S boxes. So what the problem is, that in case of output, suppose for 1 bit pattern, you are getting an output 0001. For the second different input also, you are getting 0001. So that creates a confusion in the permutation table and leading towards the next round itself. Right? So that is the issue of the second one. The third one, as you can see, it is possible to obtain same output in a single round by changing bits in only 3 neighboring S boxes. So these are like design faults which are there with respect to DES and the particularly with S box when it was conceived as the algorithm. So there is a need to change this tabulation as such. In general, that's the meaning. On the other hand, when you consider the P box, the problem is you can see the first line, and that is one of the another disadvantage of DES, that designer doesn't provide a clear idea about the initial and the final permutation. Remember, in the initial and the final permutation, I told you one table to use. But suppose that is a table that we are assuming for the time being that is a standard table. But ideally, when DES is applied or when it was conceived as an idea, there was no idea about the initial permutation and the final permutation. On the other hand, that initial and the final permutation doesn't add anything to the cryptographic solution. It's nothing to do with cryptography. Then why we are using that in the system itself is unknown. Alright, so that is one of the major drawbacks. You can see this, it will come in the next slide, it will come. So the initial permutation and the final permutation of the entire block structure. If you remember, first there was an initial permutation, then there was round 1, round 2 up to round 16. And after the round 16, there was a final permutation. So I'm talking about the initial and final permutation. There was no need of it, but it was used. So that's a redundant block which is being used and it has been standardized also. So that's one of the drawbacks of the DES with respect to S box and P box. But as I said, the key attribute to it is the key. Problem with the key. And you can observe in this particular example that in the given table, the first 4 that you are looking, that where I have mentioned the 4 out of 2 to the power 56 key, these are called as weak keys. Alright, so this, if you remember, like 2 to the power, as 56 is the total number of bits, so 2 to the power 56 will be the total number of patterns of keys that is possible. Out of those patterns, these 4 keys that you are looking at, okay, these 4 keys that you are looking at, they are called as weak keys. Why they are called weak keys? Because you can see the bottom I have mentioned the definition. A weak key is that one which after the parity drop operation, it will become either all zeros or all ones or half 0, half 1. Like that it's been mentioned over there. So it's very easy to predict. Simple as that. That's the basic logic. So you are deciphering the key very easily. So this particular 4 pattern that you are looking at for a DES is very much susceptible for intrusion. Alright, so this is the example you can see over here. They are all zeros, all ones and all that is being shown over here. So that's one of the drawback of one of the key which is called as a weakness in the key. So if suppose as the random keys are generated, as you remember in all the 16 round, random keys will be generated. So suppose in those random keys which are generated, these are the possible keys which comes up. Then basically it will create a lot of problem in the form of the next round of key generation. Because it will be easier for anyone to decipher based on that. Right? So this is one of the problem. The second one we call it that is again like taken an example over here. You can see that we are using a key which is very weak. 0101. You can see over there in the example 0101 and we are using that over here as well. The plain text was 1, 2, 3, 4, 5, 6 like this. One plain text is given. Now the cipher text, if you observe, it's got like this. Alright. Now you can see that after 2 encryption with the same key, you can see over here the same key is being used, we are getting the original plain text quite easily. So even we don't need to go for 16 round of calculation, within 2 rounds we are getting the plain text back. Then the security of the plain text is not hidden at all. The point is that. So if you are using a weak key, if you are unlucky, which is one of the factors, because DES is allowing the random keys to come in the system itself. So if suppose by randomly one of these weak keys comes into action, then basically after 2 rounds itself the plain text has been revealed to the intruders. That may be one of the scenarios. So that's why we cannot take that chance in all the options, right? So that's one of the issues with the DES. Last but not the least is called as, this is the double DES I was talking about. That 2 DES cipher you can use. So you see here 64 bit same. But in between there are 2 DES which is coming on. But even in that also, if you are using a weak key, the same will happen. And the plain text will be completely available to the intruders, given that you are getting a weak key in between. And as you know that the round key generator is an algorithm. It's not that you can control that as much. It will be generated randomly. So out of the 2 to the power 56, if these keys are generated in between, definitely there is a chance of easy decryption of the data. So it's not very secure. It's not foolproof. Okay. Not that every algorithm will be foolproof, but at least at the very rudimentary level, if it gets like within 2 rounds, if the plain text comes in, it doesn't make sense. Alright. So that's the problem. This is another part of it. It is called as semi-weak keys. Okay, another property of keys. This is where we end our discussion, in fact, for DS, because it will go on. Even the cipher will have weakness. There are other ways of doing it, but this is just for your information. If you observe over here, this is a very unique thing that is happening. These are the pairs of key, which is called as semi-weak keys. Because in this portion of it is zero, all zeros, and portion of it might be all ones, like that. And the interesting part is, if this has been used for a plain text, you can see that these are the 16 round which is given over here. Now, interestingly, what is happening, you can see the first element, first round key is actually available as the last key over here. So it's basically repeated. And also you can observe that all these keys, all these 42 which you are looking at as the last one, this is repeated over here. So at some point, the keys which you are using at the front end of the round is coming back as the next set of key at the end. So basically it's repeating. So suppose you know any of this key, and you can see it's remains same. All throughout the 8th round, it is remain almost the same. So basically the key is not changing. And even if it is changing, at some point again, you are coming back with the same key. So the key is useless. Okay. That's the problem. So with the advent of 56-bit, the problem is with the semi-weakness of the key, the 4 set of keys which are weak itself, which has all zeros and all ones, makes the vulnerability of DES to a certain extent. That's why people don't use DES nowadays. Although, as I said, there are 2 variants of it, which is a double DES or the triple DES. But as AES is already there, we don't need to do DES as much. But as DES is the first formal symmetric block cipher which was standardized, we had to study DES and the process, because AES will be on top of that. Same thing, very similar thing, except that the blocks and the operations will be different. Right? Any doubt over here? So this is just an analysis of the DES. Now let us quickly start with the AES, which is a separate discussion. As I said, it's called as the Advanced Encryption Standard, which is as you can see, the time 2001, it was standardized by NIST. This is also a symmetric key block cipher. So as per the principle of block cipher and the symmetric key cipher, it's almost the same. Alright, so it's very similar, except that it has certain attributes we need to consider. So you can observe that, and you can see that 3 areas of selecting this. One of them is the security, second is the cost, and the next one is the implementation. It is relatively simpler, you will find, to understand and to implement. But again here, the same thing, the rounds and the keys are different, but rest of the things will be almost the same. So let's see one by one what are the properties of it a little bit. So one of the thing is that it is a non-fiestal cipher. It is not the fiestal cipher, so you don't have any function on the key which controls the algorithm. So we are independent of that. So that's why it's a non-fiestal cipher that encrypts and decrypts the data block. But data block is of 128 bits. That's one of the changes. In case of the DES, it was 64 bit. Here it is 128 bits. That's one of the first change that is happening. Second property is that it might have 10, 12 or 14 rounds. Unlike to DES where it only had 16 rounds, we can have 10, 12 and 14 rounds. Now each of the round will have different set of keys. So you can see for 10, this 128, 192 and 256 is defined for the respective rounds. So this is for 10, this is for 12 and this is for 14. So 14, if you are having a 14 round, then you are going to use a 256-bit key. If it is a 10 round, then it will be a 128-bit key. And usually if that is the case, then usually there is a term of it. If this you are using, we call this as AES 128, like this is a version kind of. This is AES 192 and this is AES 256. So suppose in your question somewhere I mention it as this term, so you should be aware of that, because directly I won't be mentioning about the key or the attribute. So you have to understand that what is the number of key which are going to be used. So this is a nomenclature that you consider. right? And you can see that to create, but each version uses different cipher key. I'll show you the diagram after this. But round keys are always 128 bit. What does that mean? What does that mean? Don't get puzzled over here. Let me show you the diagram. It might be easier for you to understand. So this is my plain text. Just remember that same thing we did it for the DES as well. We had 64 bit. Now we have the rounds over here. But remember in DES it was PSTL round. Here it's a non-PSTL round. Along with all the rounds, you have something called as pre-round transformation. Now this pre-round transformation is nothing but a XOR operation. It's nothing but a XOR operation to that of the first key K0. Right? So that's the first thing that is done. For K1 to NR, NR is the capital NR is the total number of rounds. Okay? So NR is the total number of rounds that you have. So for all the other rounds, starting from K1 to KNR, okay, all these cases, the process is the same. Round 1 is there, which has certain attribute. We'll see that, how the transformation takes place. Round 1 is there, key 1 comes in, gets some operation over there, whatever the output it is, fed to the next round, and it goes on. And if you remember in DS, I told you that the last round will not have, in DS, what will not have in DS? The swapping operation. Here it will find that the last round, that is over here, it's mentioned over here, slightly different because it will not have a portion which is called as mixer. Okay, we'll see that one by one, we'll see that, but this is basically the structure. Now, if you closely observe that how many number of keys we would require, how many number of round keys we will require. So, K1 to NR, these are the generic key. Along with that, we will need a K0 over here. So, usually the formula is number of round keys. Please make a note. Number of round keys is total number of rounds plus ones. Wait, our visitor is here. Yes, right. But he's also interested in the lecture, it seems. Anyway, so we have NR plus 1 as the total round keys. So you can see in the table itself, it's mentioned if the NR is given by this, so the total key size is 128. That means here in the cipher key, you are giving as this. So somehow in this key expansion box, it will be reduced to 128 bit for 192 and 256. But for 128 bit, as the cipher key, it will remain as it is. Understand? So if it is 128 cipher key over here, and the output is also 128 bit, the expansion box doesn't have to work. But for 192 and 256, the expansion box will require to make it to 128 bit only. So the round key over here will always be 128, but the cipher key will be more than that. If you remember in case of DES, we had 56 bit coming in, but the operation wise, we are mostly using 48 bits. So very similar kind of thing we are doing. Okay. So this is basically the structure of it. And if you observe over here, there are certain definitions which you need to know, I think, before we pass on to it. So please make a note of this few things, which I would write it down here itself so that we are still in the PPT. So please keep a note of these terms. This terminology will be used at some point. So one thing is called as, this all mostly is known. So one is called, the first one is 1 byte. We will consider that always as 8 bit, which is fairly known to us. But mostly what is important, that we are going to always refer to 16 byte of information. 16 byte. So that means we are going to have 128 bits. Because 128 bits is our plain text, most of the time for our analysis later on, we will refer to 16 byte, 16 byte. So you have to mentally calculate that how many bits we are going to use. In case of DES, we are mostly doing with the bits. So that's where it is different. Another thing that comes in is called as word. One word. Okay, so this one word is called as 32 bits. This is the specification. And in case of AES, in most of the time, we are going to use 4 such words. So that means 16 bytes. So this 4 word, this word is, you will soon find what exactly is meant by word. So these are the formal few definitions that you have to keep in mind. Because we are going to use this term again and again. That's why I'm giving you over here itself. 1 bit and the 1 byte and 8 bits is not that difficult. That's okay. But this 116 byte and this word, please make a note of this too, because we are going to refer that every time. All right. So let me go back to few more things. All right. So this is where we stand at this point. So now let us quickly stay another few definitions, and for that I'll just leave out this presentation, and I'll open the word here. Yeah. So first again, sorry. So just like we have discussed the other definition, few more definitions you require, and that is first of all is called as state. So please make a note. It's very important, this word state. Okay, why it is important? Because in every case, you remember in DES we were mentioning mid bit or middle term or something like that. A black color strip we were talking about, right? In between steps in DES it was coming. Here state will indicate the same thing. The intermediate values, whichever is generated, will be considered as a state. So please make a note of it. It's an intermediate. It stores the intermediate results, and this is common to every round. It is common to whether you are generating with respect to plain text or the key. In between steps will be called as states, and that will be referred by a matrix of 16 bytes or a 4x4 matrix. So it will look something like this. The state will always be represented as this. So it will look something like this. So over here, this all will be the 1 byte. This will be my second byte. This will be my third byte. This will be my fourth byte, and so on and so forth. Understood? So this will be useful because most of the time we are going to utilize this 4x4 matrix. This is nothing to do with any specification. It's just that for AES we stick to 4x4. And remember, all those small boxes are individual byte. That means 8 bit we are considering over there. Okay? So now the thing comes in, the second one. So if you check over here, the 128 bit is taken care of. Now, specifically, if I highlight on this segment, column wise, if I focus on that column 1, this one column of each state will be called as word. So this will be called as W0. Alright. If I consider the next one, suppose this one, this is my word 1. If I consider second, third one, this will be my word 2. This is my word 3. So again, we are dividing that state into 4 columns, and the column wise information will be considered as the words. Got it? So W0, W1, W2, W2, W3, these 4 are the first initial words. Then it will go on doing something called as key expansion process, in which this keys, the initial 4 words, will be used to generate the key as well for the rest of the batches. We'll see that one by one, we'll see. But this is what the state is all about, and this part is called as word and the bytes. Now, within that also, there is some specification. So that specification, I'll mention it over here. So the first block I'm talking about, okay, the first block over here. So I'll just redraw it once again, just for our clarification. Suppose this is my box. Okay, so as per the specification, this first box will be mentioned as 0, 0. This one will be mentioned as 0, 1, 0, 0, 2 comma 0, S3 comma 0. This will be 0 comma 1, S of 1 comma 1, S of 2 comma 1, S of 3 comma 1, S of 0 2. Let me first write it down, then I'll let you know what exactly why I'm writing this way. 3 comma 2, S of 0 comma 3, S of 1 comma 3, S of 2 comma 3, and S of 3 comma 3. Now basically why I'm mentioning it over here as a separate, because just to create a less confusion in the same box. Now if you observe S of 0 comma 0, okay, this 0 that you are looking at, the first 0, okay, so this is the 0th byte of the 0th word. Please write it down. So the first left hand side 0 is considered as the 0th byte of the 0th word, W0 word, and this one is considered to be the word. So for the 0th word, there are 4 bytes each, because we have already defined that in the previous example, one word will have 4 bytes. So first byte, you can say 0th byte or first byte, whatever you call it. So this will be my consideration as 00, means the 0th byte, because we are considering in 3. You can change it to 10 also if you wish to, but anyway, let it be. So 00 is meaning for the 0th word, the 0th byte, then the second byte, first byte, second byte, and third byte, like that. So in a way, we are mentioning that this is my W0 comma 0, W0 1 comma 0, and W2 comma 0, W3 comma 0, like this. Okay, so that's how the specification works. Clear? Now, this is about the state. Now comes the key. Okay, now let's define the key. So key will be of 128 bits, suppose. We are mostly considering 128 bits because that's given in the examples mostly, and for the timing for our discussion, we are going to keep it as 128 bit. For the other two cases, 256 and 192, also it can be changed accordingly. But then since most of the cases the round key is of 128 bits, so we are going to define that in terms of 128 bits, because this is not before the round key generation. If you go back to the presentation once again, this is where we are discussing. This part is where we are discussing right now. This segment we will discuss separately. Okay, that is separate, because in that case you will have different set of keys. But how the key expansion works, we'll see it later. But for the time being, let us assume that suppose the expansion has happened, or rather the key is 128 bit key. So what will happen to that? So 128 bit key. So this will also be arranged in a key, in a matrix of this nature, same type. And each of cases, it will be like K0, K1, K2, K3. So all this you can see, again, there are 16 bytes of information we are having. So this is again a 4x4 matrix that will be considered. Alright, so this will be K4, K5, K6, K7, K8, K9, K10, K12, 11, K12, K13, K14, and K15. So the key also will be represented in a form of a state, which again will be of 4x4. Now what usually happens is that whenever we are looking at this key, and suppose I just generic way, if I tell you that how the expansion box works, or the expansion thing works, this 4x4 matrix will be converted to something like this. 1, 2, 3, 4, like that it will go on. So first one will be considered as W0, W1, W2, W3, like that. All this key that you are looking at, the K0, K1, K2, K3 will go through some kind of an expansion box. We are talking about this expansion box later, but just how this is being used, I'm talking about. So this will be mentioned as something like this. The rule is that whenever we have, please make a note for the expansion box I'm talking about. So it will be like this, W1 up to W4 NR plus 1 minus 1, like this. Like means that if we are considering 4 words over here, W0, W1, 2, 3, then basically you are looking at 44 such combinations. What we are discussing is the definitions basically. We are discussing the definition. State we have discussed. So same way we are discussing the key, that for the key also we will have kind of a state matrix which will look something like this. K0 to K15. Now the point is, if we consider the expansion box and its property, the expansion box will expand this 4 cross 4 box, and each of those column will be considered as one of this. So W0 is nothing but this, W1 is this, W2 is this, and W4 or W3 is this. Now after this there will be a certain rule through which the rest of the keys will also be generated, which we have not discussed till now. We'll see it later because it has a different structure altogether. Why I am discussing this over here? Because to understand the process of state matrix, how the matrix will look. So each of those 4 will go through certain process of sorting, and the rest of the things like W5, W4, W5 and rest of the elements, this will be repeated based on what we have over here at the initial seed. So that's the logic behind it. Okay, so this is one of the factors that we consider. So please make a note that when we have, for example, here in case of 10 rounds, so it will be 10 plus 1, 11, 11 multiplied by 4, 44. That's why the 44 keys are here. So suppose my total number of round NR is equal to 10 rounds, then number of expanded key will be of 44. Got it? So in the same manner, if the round is 14, if the round is 12, or like the one that is mentioned over there, so based on that, the number of expansion will also change. Because based on that, the state table also will change. Okay? So the definition wise, we have discussed, one is the state, very important. The state will be very important later on. And how to read the state, for each and every state, the column will be considered as one word. Now, this is, we are doing it with, suppose with respect to plain text. This diagram that you are looking at, suppose this is the plain text we are talking about. In the same manner, we can represent the key also in the same manner as a state matrix. So this will be a key generation state matrix of 4 cross 4. And in that light, we have also touched upon how the expansion box will work. So for each and every specific round, like 10 rounds or 12 rounds, the number of key sets that will be generated will differ based on the equations provided or the number of keys generated. Alright. So if that is okay with us, let us just quickly, yes please. NR plus 1. Because you are starting at 0, right? That's why. Nothing else. So now if I give you the whole diagram or the whole picture of it, which we have discussed. So this is basically the table. But if you are going by the book and the table mentioned over there, you might get confused. That's why I thought of giving you in terms of the state matrix. You can see over here what is happening. In the pre-round, this W0, W1, W2, W3. These are the words. Now we know what is W0, W1, W2, W3. Column wise, we are reading it. Now if you observe for round 1 to round NR is 4, 5, 6, 7. These are combination of words W0, W1, W3 and W4. Understood? This is my initial seed. This W0, W1, W1 and W2 and W3. These 4 words are the initial values. Based on that initial values, the other set of keys will be generated. And if you observe over here, these are some of the elements which we are looking at. Alright, so this is the 44th element that we are talking about, or the 43rd element we are talking about. You can see 10, NR equal to 10, 10 into 4 is 40, 40 plus 3, 43rd. That's what I have drawn in the earlier diagram. Alright, so this is basically the expansion process, but we'll discuss that separately. For the timing, we are not going to invest much time. Keeping that in mind, let us quickly finish off today This is the last diagram that we are going to talk about. We'll come back and we'll have to discuss this separately because this forms the crux of AES. If you observe over here, what is happening? We have a plain text here. This part, you can see this is I have mentioned as round 1. This is round 1. So within round 1, there are 4 segments which we need to understand. One is called as add round keys, which is nothing but the preliminary XORing operation with respect to K0, which we are talking about. Then we have sub bytes over here. That's one. Second, we have to understand shift rows. Third, we have mixed column over here. And finally, we have add round keys for the next round. So these are the transformation. We call it the transformation or a structure of each round. So each round will definitely have 3 segments. One is sub bytes. Second one is the shifting operation. And third one is the mixing operation. And if you observe carefully, the last round over here, the last round, the 10th round, we don't have a mixer over here, as I was telling you. Remember, I told you in the very first case that for the last round, the mixer will not be present. So you can see the mixer is not there. This diagram is for the 10th round. Similarly, for the other round, AES, there will be a little bit more, longer sequence, but the process will be the same. So next day, that will be most probably next Wednesday, because Monday I think it will be a holiday again. So you will have this segment, we will discuss this and let's see whether we can finish off today. Alright? So